Good evening. I think that by now many people have heard about the reported discovery of a new planet. And I don't mean a planet in our own solar system. This is a planet of a neutron star, something like 30,000 light years away. And this is a real surprise because a neutron star is the last kind of place where you would expect to find a planet. Two of the planets in our own solar system, the two brightest, are in the morning sky now. There is Jupiter in Leo the Lion, and lower down and even brighter, there is Venus. And these two are quite dissimilar. Jupiter is a huge body, more than 1,000 times the volume of the Earth, and with a telescope you will see a yellowish, flattened disk crossed by cloud belts. And that was a sketch I made a few mornings ago with my 15-inch telescope. Venus is about the same size as the Earth. At the moment, rather more than half its lighted side is turned towards us, but we can't see the actual surface because it's always hidden by a dense layer of cloud. Although now, thanks to the Magellan probe, we do know what Venus is like. But in our own solar system, there are altogether 9 planets going around the Sun at different distances and at different speeds. And of those, all, with the exception of Pluto, have now been explored by spacecraft. But what about planets of other stars? And here we are on very much less certain ground. Let me show you a rather interesting picture. This is a star field. In fact, it's superimposed 3 views taken over a period of several years. And since the stars appear to remain in virtually the same positions, they are superimposed. But there's one that is not. Look near the middle, and you will see 3 dots. And they are the images of a nearby red dwarf called Barnard's star, which is only 6 light years away, and does have a definite proper or individual motion against the background of more distant stars. Now, it's been suggested that as Barnard's star goes along, it is wobbling very slightly, as though it's being pulled by some unseen companion, which may well be a planet. That's the suggestion. It may well be true. On the other hand, there are doubts about the instrumentation, and we can't be sure. And certainly, we can't see planets of other stars. They are too faint and too small. But there is one other way. Cool material gives out infrared radiation. And way back in 1983, the infrared astronomical satellite, IRAS, reported cool material around certain bright stars, one of which was the brilliant blue Vega, and another was Beta Pictoris in the southern hemisphere. And there's an actual picture of the material around Beta Pictoris. There, bear in mind, that is a false color picture. So can there be planets going around these stars? Well, there could be. But again, we can't be sure, and we cannot see any planets of other stars. So how can we tell that they're there? And this reported new planet has not been seen at all. This has been detected by radio observations made with the Lovell telescope at Jodrell Bank. The leader of the team is Professor Andrew Lyne. We're delighted to welcome him back to the Sky at Night again. Welcome, Andrew. First of all, we've been talking about neutron stars, but not everyone will know what they are. So what exactly is a neutron star?
Well, a neutron star is the condensed core of a very massive star which forms after the star has burnt up most of its nuclear fuel. It doesn't have enough energy to hold itself up against gravity, and the central part of the star collapses to form this very dense neutron star. Now, it does this in a very violent explosion, and most of the mass of the star is blasted away into space. And we can see such a situation in the Crab supernova remnant here, where we see all this gas which has been blasted away. And in the center of this, there is one star which is unlike all the other stars which radiate just because of the hot surface of the stars. The radiation from this star comes in the form of pulses, 30 times a second.
And that's why these neutron stars are so often called pulsars.
Yes, that's right. They are very rapidly rotating bodies. When the core of the star collapses, so it does a pirouette in the same way that a ballerina does when she brings in her limbs and spins herself up. So the star, which might have been rotating perhaps once every few hours or once a day, ends up rotating many times a second. And they also have associated with them very intense magnetic fields, so you essentially have a very rapidly rotating bar magnet. And charged particles come out of these magnetic poles and form a beam of radio emission. Now, as this beam of radio emission rotates, so every time it crosses the line of sight to the Earth, we receive a pulse of emission from it, and hence a pulsar.
What's the real importance of studying pulsars?
Well, there are a number of reasons why we study them. their fundamental property is that they make very good clocks. They're a big flywheel spinning around, and they've got these ticks. Now, most pulsars are slowing down rather gradually as they lose energy, but we can predict exactly when pulses are going to come with a period and the rate at which the period is slowing down. We can predict a series of arrival times. Now, if we've got a good slowdown model, when we subtract these model arrival times from the observed arrival times, we should end up with 0 times. In fact, we end up with small quantities called residuals, and so from a nice smoothly rotating pulsar, we end up with a sequence of residuals rather like this, where they're mostly round about 0. This shows observations over about a 3-year period. Now, we can use this clock-like behavior to study the insides of neutron stars. They're made of some of the most condensed matter known in the universe, and it's about the only place we can really study them. Now, they're very much like an egg in that they've got a solid crust and a fluid interior. And if I can just demonstrate what happens with an egg when you spin it, you can learn a lot about what goes on inside.
A raw egg, I take it?
This is a raw egg, yes. A cooked egg wouldn't behave in the same way. Now, if I spin this egg up and stop it briefly, and then let go, you'll see something strange happening. I can get it going fast enough. I stop it and take my hand off, and you'll notice that it spins up again. And that's because the fluid inside the egg, when I stop it, the fluid inside the egg keeps rotating. I take my hand off, and the rotation of the fluid is then transferred to the egg, and it spins up again. Well, we see some of these neutron stars, or pulsars, change their rotation rate rather suddenly occasionally, particularly young ones, when they have sort of star quakes, and their rotation rate changes abruptly, and by studying what happens immediately after those, we can see evidence for the fluid inside. So we can study the material inside the stars. But we can also study things when study other situations, for instance, when they're in orbit around other stars or other neutron stars sometimes. And such studies have led to a very accurate confirmation of Einstein's theory of relativity, and have also given us the first observational evidence for the existence of gravitational waves.
Of course, at Jodrell Bank, you've been carrying out a systematic survey for new pulsars, haven't you?
Yes, in order to get pulsars in which we can do these sorts of studies, we need to first find them. And about 6 years ago, 1985, we carried out a survey in which we discovered 40 new pulsars, one of which was, 39 of them behaved fine, but one of them was rather strange. This was rotating about 3 times a second.
And this, of course, brings us on to the new planet. And at this stage, I'm delighted to introduce the other members of your team, Dr. Matthew Bales and Setnam Shima. Matthew, what drew your attention to this particular pulsar, and why is it known as 1829-10?
Well, astronomers have a coordinate system that they've applied to the sky, and it's a bit like longitude and latitude. And the name 1829-10 just refers to the pulsar's position on the sky. Now, you can see the position of the pulsar on your screen there. It's in the constellation Scutum. And I should point out that you won't be able to see this pulsar with your naked eye or an optical telescope. You can only see it with a radio telescope. And it lies on the galactic plane, and that's the white line running down the right side of the screen. Now, what drew our attention to this pulsar was that it was the only one out of 40 that had been discovered in 1985 for which we couldn't accurately predict when the pulse would arrive at the telescope. So when I arrived, the evidence, or its spin-down history, if you like, was shown on the graph here. And if it was a normal pulsar, we should have been able to accurately predict it, and all of the points would lie along the line like they do there. But instead, what we had was this rather messy plot, and we just couldn't make head nor tail of all these points. So it was decided that we should observe this pulsar much more regularly. So every day that we had the telescope, we took an observation of the pulsar, and we built up much more data. Now, it was one of our students' tasks to process this pulsar as well as numerous other ones.
And that's where you came in, Setnam. You made this very interesting discovery. Can you tell us exactly what happened?
I came across this pulsar, first of all, in May, and Andrew and I analysed some data on it. And soon after, I realised that there was a small difference for the data for this pulsar than other pulsars I'd looked at. some of the pulses in some of the data appeared to be arriving slightly early, and some pulses seem to be arriving slightly late. And I was able to draw a line through the data points and show that the fluctuations were almost periodic, with a period of about 6 months. And further analysis showed that previous data, going back to almost 5 years ago, also contained the periodic effect. I then began to think that it was possible that the pulsar had a companion, and that the pulsar was orbiting the center of mass of a binary system, and that when it was moving towards us, the pulses were arriving slightly early, and as it moved away, the pulses were arriving slightly late due to the extra light travel time. And I later found that the companion would have to be a planetary-sized mass.
Well, this is interesting, isn't it? Andrew, can I come back to you? After all, we believe that a pulsar is a supernova remnant, which is unbelievably violent. Surely that would destroy any orbiting planet.
Yes, the planet would have to survive at least 3 main hazards in that explosion. The initial one is the expansion of the pre-supernova star, when in its red giant phase, the envelope of the star would likely engulf any nearby planets and certainly cook those planets. The final collapse of the star and the resulting explosion would mainly result in the loss of a large amount of mass from the central star, or gravitational glue, and so that the orbital velocity of the planet may now exceed the escape velocity from the star, and it'll go flying off into space. The final hazard, of course, was the violence of the material which is blasted out from the central star. That's going to impact upon the planet and will certainly do it no good at all.
To get around this problem, is it possible that this particular pulsar was formed in a different way, not involving a supernova outburst at all?
Well, it's possible that the collapse was accompanied by a much less violent explosion. For instance, a star less massive than the one in the Crab Nebula probably would not collapse to a neutron star. And there's probably a critical mass somewhere between the Sun and a more massive star, where by the time the collapse occurs, there's very little material left outside the core, and so there's not much material to be blasted away into space.
But even if there has been a tremendous explosion there, is it possible that the planet was either formed later or captured later from outer space?
Yes, that seems the most likely explanation, I think, that the planet formed from a disk of material after the neutron star was formed. Normally, when a star is formed, there's a lot of other rubbish that condenses down in a disk around the star, and it's possible that planets then form and condense out of this disk to form a solar system, perhaps like our own Sun. And the same sort of a process may well have occurred around a neutron star. But it's the source of this material which is a debate. It may have come from another star, for instance, if it was in a binary system, or it's just possible that the neutron star collided with another star. This would form a thick disk from which planets might form.
Well, another thought strikes me. What we're saying really is that there's something there with a mass about 10 times that of the Earth. But can you actually say it is a planet in the accepted sense of the term?
Well, we do seem to think there is a condensed body of some sort rotating around the neutron star, but it is possible that there are other explanations for the periodicity that we've seen in the arrival times.
Well, the period is 6 months. The Earth's period is twice 6 months. Is it possible that what you're getting is a reflection of the Earth's own motion around the Sun?
Yes, it has been suggested that the delays that we've seen in the arrival times might be due to a cloud of gas, of plasma or something or other, fairly close to the solar system, but of the same sort of size as the solar system, which causes the signal to be delayed as the radiation passes through it. As the radiation passes around the edges of this cloud of gas, so the delay will be much smaller, and the pulses will arrive earlier. In this way, we'd expect to get a 6-month variation. However, when we actually compare the arrival times which we actually got, indeed the periodicity is 6 months, but there is a difference in phase between the expected sinusoid and the observed by about 90 degrees.
So that definitely doesn't work.
That's right.
Well, what about other possible explanations not involving a planet?
Well, the two other explanations have been proposed. One is that there's something to do with the fluid inside the neutron star. This isn't an ordinary fluid as we know it. This is probably a superfluid, and it may be that this fluid is sloshing around inside the neutron star, causing the crust to wobble backwards and forwards also and give rise to the observed effect. The other possibility is that the star is precessing, that the spin axis is wobbling a little bit like this every 6 months, and this would give rise to the observed effect that we see of 6 months advance and retard of the arrival times. But there would also be a couple of other observable effects. One is that the pulses would appear to have different width through the 6 months, and also that the amount of energy we received from the pulsar would vary on a 6-month period.
So all in all, you think it's a planet?
Yes.
Well, what's it like?
Well, it's, we don't know whether it's gaseous or solid. We can't tell that. But it will be receiving rather similar amount of radiation to that we observe from the sun. Roughly speaking, about a kilowatt per square meter or so is landing on this planet from the central star. This radiation isn't in the normal form of heat and light, but it's mostly gamma rays and very energetic particles, and probably would not be very conducive to life.
No, I would certainly imagine not. Matthew, are you hunting for more of these things?
Yes, at the moment we've got surveys underway in both the northern and southern hemispheres looking for more pulsars, and hopefully some of them will be as exotic as the one that had the planet.
I wonder. Setnam, you found it. What do you think you found?
Well, I have little doubt that our observations showing the periodic effect in the timing of PSR 1829-10 are correct. The simplest explanation still is that there is a planet in orbit around the pulsar. The more important question on my mind is how a planet actually got to being there.
I wonder what it is. Certainly, I think we all agree that whatever it turns out to be, it's certainly the most puzzling discovery made for many years. Andrew, thank you very much, and thank you, Matthew. Thank you, Setnam. Next month, we're going on a different kind of journey. We're going to the top of Mauna Kea, 14,000 feet up, to have a look at the Keck telescope, now the most powerful in the world. So I hope you'll join me then. And meanwhile, if you want the latest astronomical information, you can always contact the Sky at Night information line on 0898 666 000, or you can dial in for CFAX, page 616. And so, until next month, good night.